in listen-only mode.
Welcome to Westpak's webinar on product and package shock testing. I'm Greg Swinghammer. I'll be your moderator and webinar organizer today. Before we get started, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may minimize this panel by clicking on the orange arrow button in the upper left-hand corner. You may expand the panel by clicking on the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We will be answering a few questions during the webinar. However, if we are unable to address your questions during the webinar, one of our presenters will follow up with you via email afterwards. Today's webinar and video slide deck should be available on Westpak's website tomorrow. With that, let's get started. Today's presenter is Herb Schueneman, founder and chairman of the board of Westpak. Herb, take it away.
Thanks, Greg, and I'd like to welcome you all to this webinar covering product impact on shock testing. Before we begin, I'd like to make sure that everyone understands that this is intended to be an in-depth coverage of the whole idea and concept of shock testing. It's my intention to cover this area maybe slightly beyond the scope of one's normal job function so that perhaps a better foundation and understanding might result. This is one of my favorite areas, the shocking truth, if you will. So I'm certainly glad that you're joining us on this brief excursion, and I hope the journey is a good one for you. Here are the areas we'd like to cover during this all too brief excursion into this realm of shock testing. First, we'd like to discover why we test products and package systems for mechanical shock sensitivity in the first place. What do we expect to learn from this? We'd also like to know how, when, and why we conduct the testing. What are the procedures that we use? What equipment is required? When in the product development cycle is this information most relevant? What are the important steps? What are the pitfalls to be avoided? Finally, we want to go thoroughly through and examine what we do with the information once we obtain it. This is not just an exercise in running a shock test machine or drop tester. There is a good, logical, and economically beneficial series of reasons for conducting this testing, and we intend to investigate as many as we possibly can. In order to achieve our objectives, we'll follow this agenda. In order to get the lingo correct, we'll delve into the terminology of shock testing after we've got a brief understanding of how this testing got started in the first place. As we have mentioned before, it's important to know the lingo in any professional endeavor. This is the corridor through which professionals in any particular area communicate. So if you want to live in Brazil, you'd better know Portuguese. In the same way, if you want to exist in the world of shock testing, you have to know the lingo. We will then go into shock dynamics in a big way. I will talk about exactly what is a shock input or pulse, what constitutes product fragility, what are some methods of obtaining product fragility information, what we can do with the information in terms of product modifications, what are some different approaches to shock testing. We will explore some common myths involving shock input, and we'll take an in-depth look at how cushions mitigate shock input to products during transit. Many people question the exact difference between shock and vibration input. In both cases, one can trace a mechanical input in terms of its amplitude and duration. This is referred to as a time domain event. That is, there is some excitation occurring over some period of time. In the case of vibration, the event is continuous. In the case of shock, it is discontinuous. That is, we can clearly define the beginning and ending of a shock event. In this regard, shock can be considered a subset of vibration, and we will treat it that way during this webinar. refer to our previous webinar on vibration dynamics for more information. This one, as all our webinars, can be found on our website. It's important to remember that shock is a vector quantity, which means it has both magnitude and direction. And both of these are important. The amplitude of a shock input is normally in terms of acceleration, that is typically measured in multiples of Earth's gravitational constant, a quantity we call g. The amplitude of any particular shock pulse is normally characterized in terms of uppercase g, which are multiples of the Earth's gravitational constant. In addition to the peak amplitude of a shock input or pulse, we are also interested in the duration of that shock event and the shape of the pulse itself. We normally define the pulse shape as a half sine wave or triangular wave or trapezoidal shape or complex shape or similar. We can also define a shock pulse in the frequency domain as opposed to the time domain. The frequency domain is simply the inverse of the time domain, in which we talk about amplitude versus frequency as opposed to amplitude versus time. When using the frequency domain, a shock pulse becomes a shock spectrum. We talk a lot more about that shortly. Now that we have at least some of the lingo under our belt, let's look at some of the interesting background information. For most products, the most shock-intensive portion of their entire life cycle is during the delivery and transit events. Shock is largely a people event. That is, people drop things, creating shock inputs. There are some exceptions to this, for example, in the military environment, but for the most part, the shock occurs because of people's actions. The reason why we shock test products is because we want to deliver a quality product to our customer, and we know that the customer is on the other side of that delivery and transit environment that is full of shock events, or might I say shocking events. Knowledge of shock testing and shock fragility in particular is absolutely essential to the process of delivering a quality product to your customer. No doubt you've heard about people who think shock testing is extravagant and wasteful and is a function that should be ignored. I like to point out that your product will always be shock tested. Okay, the distribution environment will make sure of that. It never fails. Let me repeat, your product will in fact be shock tested. The only question remaining is, who sees the results first, you or your customer? The importance of shock testing and product ruggedness is becoming more important in today's global distribution society because the length and severity of the distribution environment seems to be getting worse from a shock and vibration standpoint. Smaller and lighter weight products are also easier to toss and drop, thus creating a more severe shock environment in that regard. It appears that the trend continues in the same direction, and that is products are being made globally and distributed globally as well. Products are getting lighter and thus easier to subject to shock inputs. The emphasis on product quality is also increasing. All of these trends would lead the astute observer to believe that shock testing of products and the resulting product ruggedization or improvement are becoming more and more important. To better understand the concept of shock mechanically, we bring back our old buddy, the spring mass system. This model was highly developed in our previous webinar on vibration testing, and I would encourage those interested, again, to review that information, which is readily available on the Westpak website. We call this model a single degree of freedom system, or SDOF for short. Briefly, the model consists of a foundation of infinite mass on which is attached a spring with a known stiffness, or what we call a spring rate. Attached to the top of the spring is a mass of uniform density that is constrained to respond in one axis only, in this particular case the vertical axis. Often some level of damping is included, but we have not shown that in this particular model just for simplification. Also implied in our model is the ability to measure the acceleration input at the foundation and the acceleration response of the mass. That is what's shown here, the acceleration input at this location and the acceleration response here. So when we talk about the numbers and we talk about input versus response, that's what we're talking about. Assume that there's an accelerometer at the point AR and that it's measuring the response, and that there's a similar accelerometer at this point, A sub I, that measures the input. It turns out that there are two very distinct methods or manners in which this spring mass model or system responds to a shock input. Much of this difference depends on the duration of the shock input, or what can be thought of as its frequency, which is essentially 1 over the duration, relative to the natural frequency of the spring mass system. Again, if you want to define the natural frequency, refer to the previous webinar on the Westpak website. In the first case, or what I would call the type 1 response, the shock input is very, very short relative to the natural period, which is 1 over the frequency of the spring mass system. In other words, this shock input pulse is just so fast, it's too fast for the system to respond to it. So this type of input is often called a velocity shock. The response of the spring mass system is independent of the input wave shape or peak amplitude. So that's what we call a type 1 response, right here. A type 2 response, okay, in this particular case, the pulse is of a long duration, long enough so that the spring mass system can respond to the pulse shape, its peak in particular. So long enough in this case means that the period of the input pulse is 1/2 or greater the period of the response. Okay, so the period of the input pulse right here is 1/2 or greater the period of the response measured here. For example, if the input pulse duration is very short relative to the natural frequency of the spring mass system, then the ratio of the frequency response divided by the frequency of the input is very small. Okay. On this particular chart, that small number is shown here. Okay. So in this particular case, the ratio of the response to the input is 0.25 or 1/4. Okay. So the result is that you have a very low response. If this is the input pulse, the response here shown in the red dashed line is relatively low relative to the input. Okay, so even though the input's at some level, the response can't keep up with it. That's what it's trying to say. As the duration of the shock input increases, and therefore the ratio of the response to the input increases, the amplitude of the response also increases. You can see that in this next diagram here, where the ratio of the response to the input is 1/2. We see that the input pulse, in this particular case, this trapezoidal pulse, or this triangular pulse, the response is actually greater than the input, so it's amplified. And the only difference between those two is that now the ratio of the frequency response to the frequency of the input is greater or equal to 1/2. Okay. In fact, the maximum amplitude of the response occurs with a frequency response to frequency of the input ratio of 1/2. You can see that on this diagram. After that point, the amplitude is a maximum for that particular wave shape as the duration of the shock pulse continues to increase. So again, that is shown here as the ratio between the response, f sub r right here, to the input, frequency of the input right here. As that ratio continues to increase, okay, we see that the amplitude remains approximately constant for that particular wave shape. The frequency of the response is exactly the natural frequency of this spring mass system. Okay. A similar thing occurs with other pulse shapes. As you can see in this particular slide, the rectangular or trapezoidal wave shown here, rectangular wave in this particular case, okay, the response peaks out also at a ratio of the response to the input of 1/2 or greater. Okay. For this particular wave shape, the peak amplitude of the response can be double that of the input. Okay, so the response here can be double that of the input. The second set of plots down here on this screen shows that the response for that same spring mass system to a half sine input. As before, we see that the maximum response occurs at a response input ratio of 1/2 or greater. In this case, the maximum response amplitude is approximately 2/3 of that of the rectangular pulse. Okay. So once you're beyond this ratio of 1/2 response to the input ratio of the frequency, the responding system, the amplitude of that responding system is really a function of the wave shape and its frequency content as well. Here are the things that we should remember from this brief dive into shock response spectrum analysis. Regardless of the wave shape, when the duration of the input is very short relative to the natural period of the response, the response is only a function of the velocity change of the input, not of the wave shape, peak amplitude, or anything else. The velocity change is the area under that acceleration versus time pulse. It can be thought of as the energy content of the pulse, although it's not really energy because there's no mass involved in it. As the duration of the shock pulse approaches 1/2 the natural period of the responding system, the response of the spring mass system reaches its maximum for all wave shapes. Okay. The maximum response is produced by a square, or what we refer to as a stepped input, often called a square wave. It's really a trapezoidal pulse. And then all other wave shapes produce a response of the spring mass system that is less severe than that of the trapezoidal pulse. This sequence of input on the top and response traces below them show how these systems look like in the real world. On the first screenshot on the upper left, okay, one sees that an input is fairly short relative to the response below it. So what does that mean? It means that the duration of this input is relatively short compared to the duration of the response below it. These are both on the same time scale. You can also see that the response is out of phase with the input. In other words, the response doesn't start until the input is nearly over. Okay. So that defines a system that is responding to the velocity change of the input. In other words, the area under this acceleration versus time pulse, rather than to its peak pulse here, because this peak is very much higher than this peak. Okay. The following plot shows a slightly longer duration pulse with an input that is still of higher duration than the response. So this input here is a higher frequency, shorter duration than the response here. But you can see that the amplitude is in fact building up, and the phase relationship is getting a little more closer to being in phase. The system is responding quicker to the start of the shock input. Okay. The next pulse shows the beginning of a trapezoidal pulse with a response below it that is clearly of higher amplitude than the input. Okay. So here's our trapezoidal pulse with a mean or a faired acceleration level here, but you can see that the response is now double the input, and so we have crossed our 1/2 threshold between the frequency of the response and the frequency of the input. So you can see that the input here, this is the natural frequency of that spring mass system. The peak amplitude here is about double the faired peak amplitude here. We'll also notice that the phase shift between the response and the input has become less and less as the input pulse duration increases. This is another way of saying that the spring mass system can actually respond to the shock input as well as the input becomes closer and closer to the natural period of the spring mass system. The remaining plots here show that the amplitude of the response continues. So it continues at this max response level as this duration of the input continues to increase. Okay, so here you see the residual spectrum being diminished, but the actual primary response is still peaked out. We'll talk a little bit about the residual spectrum later, and if anyone's interested, that's the subject of the advanced class in shock response spectrum analysis. If we plot the response of our spring mass system to the various types of wave shapes that we have described previously, we will see the following. Okay. Notice that these plots show the amplitude of the response. Okay. Amplitude of the response on the vertical axis divided by the frequency response over input ratio on the horizontal axis. These are typical formats for shock response spectrum. We can see that for this, what's referred to as a square or trapezoidal pulse, we can see that the response again reaches a maximum at a frequency response input ratio of about 1/2, somewhere in that area, and that it reaches a maximum amplitude of twice the input and remains that way for longer and longer durations or higher and higher ratios of the response to the input frequency. For this half sine shock pulse, okay, we see that again the maximum response over input, the maximum response of the spring mass system reaches its peak value at a frequency response over input ratio of about 1/2. Okay, and that the peak amplitude of the response is about 1.7, 1.8 times the input. Okay, again, these are for theoretical systems. And then for a sawtooth pulse, in this particular case a terminal peak sawtooth pulse, we see a similar relationship, except that the peak response reaches a value of 1.5 times the input. Okay, so and these are all assumed to have the same duration input pulse. Okay. If we combine all of these plots into one shock response spectrum plot, the theoretical one, we will get something that looks like this. Okay. In addition, we can see that the velocity shock region here, okay, in the lower left portion, while the remaining responses are in what we refer to as the acceleration region here. So velocity shock means that the spring mass system is only responding to the velocity change or energy content of the pulse, and in the rest of the region it's responding to both the peak acceleration and the wave shape. So you can see that if we put all these in the same way, this is obviously not accurate for the half sine and Sawtooth pulse, but you get the idea. They reach a peak at a ratio, frequency response input ratio of 1/2, and that the half sine has a complex relationships. After that, the trapezoidal pulse and the square wave both have flat responses. The theoretical square wave has a flat response. The trapezoidal pulse actually has a sloping down response, but nothing we can't live with. If you ever see that, don't let that bother you. The important thing to remember here is that there is such a thing as a velocity shock region of the SRS, and that occupies this area here, and that there's an acceleration shock response region, and that occupies most of the other area. In fact, all of the other area of the SRS. And again, where these numbers come from, the acceleration response right here, acceleration input right here, okay, frequency of the response right here, okay, we simply count the number of cycles per second, and the frequency of the input right here, okay. Normally the frequency of the input is simply the inverse of the duration of the shock input pulse. Now that we have this background information under our belts, it's useful to re-examine the purpose for shock testing in the first place. Clearly, the purpose is to determine the fragility of products, that is, their maximum resistance to shock inputs. This characteristic is desirable for both the in-use environments of the product as well as the delivery or distribution environments where shock levels are normally much higher. It's also important to recognize that shock testing can be extremely useful to improve the ruggedness of designs and add value to the product. It would be hard to overstate the value of a ruggedized product, especially in a highly competitive environment. The reason why we focus on shock response spectrum analysis is that we now know that the response of any product is going to be more severe when the shock input is a trapezoidal shaped pulse. This information will be very useful to us very shortly. Back in the dark ages, I'm going to call them, fragility testing typically used these SRS techniques simply because we didn't have a good knowledge of what inputs were likely. In addition, shock testing had its origins in architectural field primarily for designing and bridges and buildings to withstand seismic events such as earthquakes. It would be very difficult to put a building on a shock test machine and determine its fragility. So architects used a response spectrum to analyze a structure rather than relying on an input shock pulse to determine how fragile the building was. So the shock response spectrum is rather complex and time-consuming, and a simplification was absolutely essential if effective and meaningful shock testing was to be conducted on products at any significant level. So shortly we'll examine a much more simplified approach to shock testing, but one that's much more productive as well. So hang on to your hats. Just when things were looking very complex in the area of product shock testing, our good old friend Dr. Robert Newton came up with the damage boundary theory to help simplify our lives and make product shock fragility testing much simpler. Dr. Newton recognized that there are two primary tests involved in fragility testing. One is this type 1 response here, and the other is the type 2 response. Type 1 response could be investigated using a short duration half sine pulse because the waveform was not important. Type 2 responses here could be programmed with a trapezoidal pulse to determine these responses at a conservative level. In order to help avoid confusion, he also designed the damage boundary plot to look different than the SRS plot. This is the typical damage boundary plot shown here with a peak acceleration on the horizontal axis, and velocity change on the vertical axis. Okay. Velocity change is, again, the area under the acceleration versus time pulse, and can be thought of as the energy content of the waveform. Isn't exactly that, but it can be thought of that way. To conduct a test, the procedure calls for fixturing a product on the table of the suitable shock test machine and subjecting it to a very short duration pulse. In this particular case, a half sine is used because the shape of the pulse is not important. Okay? We typically use 2 to 3 milliseconds for those durations. The procedure calls for increasing then the velocity change, or the area under this pulse, in small increments, and since the duration of the pulse is held constant, if you're going to increase the area, you have to increase the peak. So that's why these individual lines step upwards. Okay, so you keep programming pulses into the product of higher and higher velocity change, okay, until failure occurs. Okay. The last non-failure input is normally then defined as the critical velocity change for the product in that orientation. Again, and this was came from the shock response spectrum analysis, because this short duration pulse determines the response of the product in the velocity shock region of the SRS. Okay. In order to conduct this test, then, a new product is fixtured to the table of the shock test machine and subjected to a longer duration pulse, and we typically use a trapezoidal pulse with a relatively low acceleration, low compared to the velocity change pulse for sure, okay, and at least double this velocity change. So the area under this pulse is at least double the area under this pulse. Okay, so that particular pulse can be programmed or plotted on this damage boundary as a low acceleration level, okay, but a higher velocity change than the previous test. Okay, the product is checked for damage, and if no damage has occurred, a slightly higher acceleration pulse is programmed with approximately the same velocity change. So the area under this pulse stays approximately the same, but we're increasing this amplitude level. And we keep doing that with the same product and checking for a failure until a failure occurs or damage of some sort occurs. So this the last non-failure or non-damage producing pulse, or in this case the mean between those two, then determines this so-called critical acceleration for the product. Okay, so that's the nut and bolts of this so-called damage boundary test. And again, both of these inputs come directly from the shock response spectrum analysis, and it was the genius of Dr. Newton that actually gave us this simplified method. Even though most of us have lived with the damage boundary for a long time and consider it to be a very standard test procedure, in reality, the approach Dr. Newton suggested was both simple and brilliant. The critical velocity change determined from this procedure, which is later published as ASTM D3332, told the product designer how high the unpackaged product can fall onto a rigid surface before damage was anticipated. Note that the velocity change is directly related to free fall drop height. We'll see that in a minute. The critical velocity change was likely, if that velocity change was likely to be exceeded during product in use or distribution environments, then modifications were necessary in terms of the product design, or a protective package was necessary for shipment of the product, where the ruggedness of the product did not meet the demands of the distribution environment. Let's return to the critical velocity change and go through that exercise as I previously promised. The critical velocity change is determined from test results and tells us the maximum drop height that the product can bear before damage occurs. So this is experimentally determined from the damage boundary test, and it results in this so-called velocity change. But velocity change is also equal to 1 plus a quantity E, I'll talk about that in a minute, times the square root of 2 times acceleration constant times the drop height. So E is the coefficient of restitution of impact surfaces. What the heck is that? Coefficient of restitution measures the amount of energy that is either dissipated by the impact surface or absorbed by it and then given back to the product. So it's equal to the velocity of the response of the product to the velocity of the input. So you can actually measure those as well if needed being. But that's that. We know that all surfaces produce an E value of greater than 0 and less than 1. So we can use a medium value of 0.5, for example, to estimate the drop height that's going to occur with a given experimentally determined velocity change. And again, the gravitational constant is exactly that, a constant, 386 inches per second squared, or 9.8 meters per second squared. And so you can solve this equation for the drop height, and with some estimate of what the E might be, you can determine what that critical velocity change really means in terms of product ruggedness. For example, let's say a product had a critical velocity change of 100 inches per second. Okay, if we solved this equation for H and substituted 100 inches per second for the velocity change and assumed that the coefficient restitution is going to be 0.5, that would be typical of a carpeted floor, for example. Okay, then we know that the drop height is going to be somewhere in the neighborhood of 10 inches or so. We can actually do that math, but you can see how this experimentally described or derived velocity change is going to give you a drop height that is very useful in terms of product ruggedness. It's important to note that there are a number of methods for determining the fragility of products. I dwelled on the damage boundary, but I've used all these methods at one time or another, and some are okay and some are not okay. I've never seen a better procedure for fragility assessment than the damage boundary test procedure just described. While there are some significant problems with damage boundary procedure as presented, it is far and away the best procedure that exists today for the purpose of determining product fragility and product reliability analysis as well. Highly recommended. Regardless of the procedure utilized, the end result of product shock testing should be a more reliable and robust product. In addition, one can easily identify where it's likely to fail or where other deficiencies in the design could be improved. You'll be able to determine if the product meets customer demands, and it's likely to have it's helpful to have warranty claims above the tolerable levels as well, obviously. It's very significant that in this age of shipping products globally, this type of procedure is the best one known to allow for the optimization of the protective package system, which for most products results in a far lower overall delivered cost. Sooner or later, product costs determine their ability to be a viable and long-term product in the marketplace. For globally distributed products, distribution often represents 35% or more of the cost of a quality delivered product. Think about it this way: if you improve or let's say improve the cost of a product by taking 50% of the material cost out, you'll probably only save a relatively small quantity because the material costs of most products are relatively small compared to other portions. But the delivery costs, which include packaging, often represent 35% or more of the cost of a delivered product. And if you can improve that by 50%, you're saving a lot of money. So costs are the biggest reason why we'd like to have a more rugged product. There are some interesting notes that should be understood relative to shock testing. First of all, this is a destructive test. Products are taken to the failure level in order to determine their fragility. It's also interesting to note that a rigorous test would involve 12 specimens. That is, one for each flat face of the product, top, bottom, left and right, front and back, and then one for velocity and one for acceleration testing for each orientation. Okay. The test results are highly dependent on good fixturing of the products during the shock input. This can be tedious and expensive at times, but it's often well worth it. It's also worthwhile noting that the use of the trapezoidal pulse for critical acceleration testing is conservative. I mentioned this before. This means that the package system designed with this testing may be somewhat conservative and perhaps over-designed. In addition, the design numbers given during the damage boundary test are input numbers for a shock test machine because they come from the shock test machine. During a package performance test, the only thing that we can really measure is the response values, and these might be quite different. There are ways around this particular issue, but it's important to recognize that there is a difference between shock input and product response. I always have a good time talking about the various myths that have developed around shock testing in general. And one of these myths is that the 11 millisecond shock pulse represents kind of an ideal pulse. It turns out that the 11 millisecond pulse came from, of all things, an old shock test machine. It was a Berry sand dropper, in fact, and there are a lot of myths about it, but the story that's often told is that the shock pulse produced by this particular machine was so noisy, as you can see in this generalization here, that no one could figure out what the exact duration was. And for shock response spectrum analysis, you better know that frequency, which means you have to know the duration. Okay, so because they couldn't agree in this particular laboratory about who was right or wrong or whose judgment would be best, the person of the highest rank said it's 11 milliseconds because I said so and no one overranks me, so just use that. And that's about as good as an excuse as I've heard about where this 11 millisecond comes from some old mil spec testing. So don't fall into the trap to thinking that you have to go to a mil standard and use their 11 millisecond duration. It really has no particular value other than it sounds good, I guess. I don't know. Other myths are important too, given that we've previously shown that this half sine shock pulse myth, one could easily question why the half sine pulse is used at all in the process of fragility assessment, reliability testing, or anything else. Remember that its response spectrum was less intense than that of the trapezoidal pulse. It turns out that the half sine pulse is very easy to program on shock test equipment. Seen here are some of the programmers that are actually used. These are what's referred to as modules, and they're simply cushions of varying durometer and thickness, and they're stacked up under the table of a shock test machine and used to program half sine pulses. Turns out that this makes it very easy to program, and that many shock pulses seen in the environment have kind of a half sine-ish shape to them, which there's a kind of an appeal to that, probably because it resembles a normal distribution curve or something. I'm not sure. But there are some serious problems with the half sine pulse when used for fragility analysis. This pulse excites only the odd harmonics within a product. You saw that the response spectrum from the SRS was kind of scalloped, And if you look at it and do the math, you'll see that those are the odd harmonics within a product that are causing the excitation. So it doesn't really represent the maximum response of a product to a given peak duration and amplitude of a pulse. In addition, it doesn't represent the worst amplitude case for the same peak and duration of an input. So it has some serious drawbacks. There have been reports of people programming the duration of a half sine pulse in order to get into some of those reduced portions of the spectrum, and in order to have a product pass a certain test where it really is not that rugged. So don't think that the half sine is the do all and be all. I mentioned the Sawtooth pulse. This is one that's not real common. So many people ask, what the heck is that? It's recognized early on in shock response spectrum analysis that the even and odd harmonics, as I mentioned earlier, play a role in how a product fails in response to a shock input. And I mentioned earlier that the half sine pulse will excite the odd harmonics in the residual spectrum of a spring mass system. Well, in a similar way, a terminal peak sawtooth pulse will excite the even harmonics within the residual spectrum of a spring mass system. So you actually need both of those in order to be a conservative. Turns out that the square wave does that. But anyway, this terminal peak sawtooth found favor with the military testing early on because of the similarity in shape to that discovered from ordnance impacting. That is, if you look at what happens when a bullet strikes an armor plate, for example, it might look more like a terminal peak sawtooth than anything else. So this type of pulse was used in that regard, but it's rarely found in the so-called commercial marketplace. Finally, let's take a look at some of the myths involved with a square or trapezoidal pulse. This one. In the first place, there's no such thing as a square wave because all pulses must have a finite rise and decay time. Okay, the best we can do is this trapezoidal pulse. So the two terms, square pulse and trapezoidal pulse, are often used interchangeably, even though they're not really interchangeable. There's many things to like about this trapezoidal pulse. It's easy to program on a shock test machine. We simply use these cylinders here. These are pneumatic cylinders with a piston on the top, and these pistons are then impacted by these plungers as the table on the shock machine falls. These plungers are mounted on the bottom side of the shock machine, and they strike the pistons, and underneath them are nitrogen gas, which you can control very precisely. So you have everything you need. You control velocity change by the drop height of the shock table, and you control peak acceleration by the pressure in the cylinder. It's very easy to do. Okay. So they're easy to program. On the negative side, this trapezoidal pulse is conservative in that it's rarely seen in the real world environment. It's also difficult to achieve very high acceleration levels because you simply can't get enough nitrogen gas into the cylinders. Given all the pluses and minuses of this so-called trapezoidal pulse, it still represents the best and most uniform approach for shock fragility testing. Interestingly, even though Mil Standard 810 incorporates the trapezoidal pulse as a standard shock test method, it's still not widely utilized in military test applications. Since much reliability testing had its origin in mil-spec applications, common reliability testing somewhat shuns the use of this trapezoidal pulse, although the trend is diminishing. The guided shock test machine showed here is by far the most common, and is typically equipped with a short duration half sine and longer duration square wave pulse programmers. So you see those here. These black cylinders are the half sine programmers, and these tall cylinders are the trapezoidal shaped programmers. Another significant use of shock testing involved the characterization of the shock absorbing cushion materials. The reason for this testing is to determine what type of material and what thickness and the proper loading of the material in order to produce the kind of shock protection necessary for a given application. There are several different procedures that are very common in this area, and the choice of the procedure depends primarily on the type of material being utilized and the application for the data. By far the most common application is the ASTM D1596 procedure. In this procedure, the cushion material is impacted with a platen of known mass and known velocity. The actual procedure looks like this. The end result deceleration level experienced by the platen is recorded. This procedure is repeated a total of 5 times, and the mass of the platen is then changed in order to change the static loading, and the process is repeated. The results of this test are a cushion curve such as shown here. It describes the peak deceleration as a function of the static loading on the cushion. The cushion curve tells us that a relatively light loadings, at light loadings, the deceleration level transmitted through the cushion is fairly high. In other words, the cushion can't deflect. There's just simply not enough energy to do that. As the loading on the cushion increases, an optimum range is reached where the transmitted deceleration level reaches a minimum. As the mass or loading on the cushion continues to increase, we see an increase in acceleration level because of the so-called bottoming of the cushion. Obviously, it's desirable to design and use cushion materials in the optimum range, often called the belly of the cushion curve, right here. Regardless of the procedure utilized for cushion material analysis, the cushion curve shown on the previous slide will always display peak acceleration or deceleration on the vertical axis and static stress or loading on the horizontal axis. Note that static stress is equal to the weight on the cushion divided by its bearing area. So if you had 64 square inches of bearing area and a 64-pound product, you would have 1 pound per square inch, or 1 psi. Static loading and cushion thickness are the primary variables used in optimum protective package design work. The cushion curve data is conservative because of the requirement to impact the cushion sample 5 times at each static stress loading. For this reason, it's often possible to achieve results that are better than those predicted by the cushion curve, based solely on the conservative nature of the cushion. It was mentioned earlier that the most desirable place to load a cushion is at the so-called the belly of the curve. Presented in this way, the cushion curve gives a very good indication of exactly what thickness of cushion is necessary and the proper loading on that cushion in order to give the desired protection level for the product with a known fragility. So if you've previously done your fragility analysis, you know exactly what G level the product must be protected to. So if this is the anticipated drop height in the distribution environment, and that's the known fragility level, you know exactly how thick a cushion and at what loading, how much weight per unit area you need. Since the weight of the product is given, it then tells you exactly how much area of cushion will give the results that you're looking for. It's important to recognize that this information, and especially the presentation of the information, is a relatively recent phenomenon. Prior to the 1970s, for sure, it was difficult to scientifically design a package system because of the lack of good information on shock absorbing characteristics of available cushion materials. Protective package design was more art than science. Since the widespread use of cushion curves, optimum package design has been within the easy grasp of engineering professionals. Here's an example of exactly how this cushion curve is used. Suppose that we have a product of a known fragility level, and let's call that 28 Gs. Okay. If the cushion material described by this a cushion curve is utilized, whatever that happens to be, okay, then we can draw a horizontal line across this plot at the fragility level, and it tells us that we can use this thickness of material, 6 centimeters in this particular case, over the bearing area between 36 and 66 grams per square centimeter. The optimum loading for the product would be in the neighborhood of 52, right about here. Okay. Remember that the loading on the cushion material must satisfy both shock and vibration requirements for the product. In a previous webinar, we discussed designing a cushion system for proper vibration protection of vibration-sensitive products. It's important to remember the cushion system must provide both the shock protection, shown here, and the vibration here, and sometimes these loadings do not coincide. Okay, so the process for actually designing and testing that package system has been covered extensively in previous webinars. In particular, we would direct your attention to the Packaging Dynamics webinar number 5, presented in 2015 and available on the Westpak website. Well, we've covered a lot of territory here, and there must be some questions that some of our loyal attendees can think of. Before I address these questions, I should point out that this information is not particularly easy to absorb, and that everyone who presents it does so slightly differently. I hope that this hasn't been confusing, because I continue to strive to make this material more easily understood by what I consider to be normal or average practitioner. Some may consider this to be a rather remedial exercise, and others may consider it to be way too technical. I strive for a balance somewhere in between. So, Greg, are there any questions that I can address?
Thanks, Herb. That was an excellent webinar. Excuse me. Thanks, Herb. That was an excellent webinar. Thanks for the valuable information. However, due to the length of the webinar and the depth of the webinar, we don't have time for questions right now. Thank you all who sent in questions. Herb or someone here from Westpak will follow up with you on those questions. If you have any other questions you think of later, you can submit them to our website at www.westpak.com/contact us. There will be answers either by Herb or someone from our team later this week. Thanks for understanding the situation. Keeping our time commitment with you is our goal. Westpak's next webinar is on June 16th and is titled Riveting Revisions of Medical Device Package Testing Procedures. I think they put that name together just to make me have to stumble through the words, but it'll be presented by Ms. Katie Tran, who's a lab manager here at Westpak. If you are in the medical device industry, this is a good webinar to listen to because it has information on updated standards. You can register for either one of the webinar sessions by accessing the webinar page on our website to find the announcement, or we will be sending out a personal invitation here shortly. We have 2 locations, one here in San Jose, California, and one in San Diego, California. Please contact us and let us know if you need any help, whether it's with questions for testing, quoting, or a need for information about Westpak. If you missed anything or would like to listen to the webinar again, please go to Westpak's website at www.westpak.com under the Resources Webinar tab. The webinar materials should be uploaded by Tuesday. We will be sending out a short survey within the hour. Please fill it out, as we highly value your opinion regarding today's webinar. You also have the opportunity to ask more questions at that point if you think of stuff later. Thanks for attending. I'm Greg Schwinghammer. Make it a great day.